Yeah, I'm trying to see why.
So I can hear you now.
Can you hear me?
Yes.
Yes. Okay, okay. Because I don't understand what's happening here. Okay, can you guys also see my screen?
Yes, sir.
Yeah, and I can see there's someone else claiming that they can't hear me. Okay, guys. So basically going to continue with machine learning. Before we can start, is there any question? Any question before we start? Okay. All right. No question. Remember last week we said the first question you ask yourself is what problem am I solving? Once we get what problem we are solving, then we will know which algorithm to use, which of learning we're going to use, which will determine which type of algorithm we're going to use, right? So if we identify the problem as a classification problem, this means that we're going to use one of the algorithm that has to do with classification. That will depend on the type of scenario that we have, right? If we identify that the problem is a regression problem, then we're going to go with a regression algorithm, all right? And if we are dealing with the clustering problem, we will choose some of the algorithm. Okay, so we're gonna go through this algorithm here, so we can see how do these algorithm work, what do they do. Then you can see, okay, if this is the right algorithm for your scenario. Okay, so we started with linear regression. What we said, linear regression is just an algorithm that will be used for regression problem, and when we're using supervised learning. So what is this that you can see here? Can anybody tell me what are these blue dots here and the red dot? What do they represent? What do they represent? What do they represent? Anyone? Anyone understand what they represent? Or is there anyone who does not know what they represent?
Are they numbers? So
No, they are not numbers.
Isn't it a data that they were trained on, or maybe the data on the model?
Yeah, those are the training data. Which means this. It means, let's say, in this case, here we have, in this case, we have something like, let's say, for example, you are trying to, these are the data that you have. So basically, maybe, let's say you want to see the numbers of kilometers that people take on a certain road, for example. But instead of you just estimating, taking an average, you can create an AI that can determine that by knowing the speed of the person and the numbers of kilometers that were taken. So let's say, for example, this is the speed. So let's say this is 60 kilometers per hour. When a person was showing us 16 kilometers per hour on our road, so 60 kilometers, you see this data here, maybe 60 kilometers gave us something like maybe 60 kilometers per hour, we only travel maybe 12 kilometers. Can you see? So it's basically this data, the information of this data here. Let's say this is the distance, this is the velocity, the speed. So the information of this will be something like 12 and 60. So this is the information of this point here. So if we are given the data in a table, this is what we're going to have. For this data here, we're going to have 12, 60. This is the distance, and this is the speed. So we have the 1260 here. Maybe this one here will be maybe a 30 and then 5, something like that. So we have, when we have 5 here, we have 30 kilometers per hour. Can you see? So now all these data have their own information. All these are samples. So this point here represents samples. So based on this now, we can create a model. And the model we create is this one, this line. This is the model that we're going to create. That means that every time we're going to use this model by just writing the information about the distance and information about the speed, and then we can predict whatever we're trying to predict. Understand? So that is a linear regression. A linear regression means that the final model that we get, remember, the model is a mathematical formula that has been created by your data in order to predict future data. Okay, so now looking at that, now we understand that linear regression, this algorithm will give us a model which is just a line represented by a line. So it's if you look in mathematics, the equation of a line is represented by y. If the line is y, it's going to be ax plus b. And in this case, we're going to have the weight, right? The weight parameter and the bias parameter. Okay, so this is our model, the equation of our model. But when we train our model, because the model cannot be perfect, on this equation, we're going to add the error. So the whole point of machine learning will now be to changing these parameters, bias and weight, in order for us to obtain a small error. And to obtain the small error, we're using depending on the scenario, depending on the algorithm we use, we have what we call a loss function. So this is a loss function in a linear regression, as we spoke about it last week. So we say as well, when we're dealing with linear regression, to avoid an overfitting problem, which means that an overfitting problem means that your data, your model has been trained with so many data. Your model is more advanced than the number of data that was used on. So you basically have a big model, you basically have a sophisticated model, but you don't have enough data. So that creates an overfitting problem. So to avoid that, we've created what we call a regularization system. So regularization system, it means we add something to regulate these parameters. Remember, these W's, the weight, are parameters. They are not hyperparameters. Why am I calling them parameter? Can anybody help us? Why are they parameters? Why are they parameters? Can anybody tell us why the weight is a parameter, it's not an hyperparameter? Why is the weight not an hyperparameter, but it's a parameter? Can anybody tell us? Anyone?
I'm not sure.
Okay.
I am not sure, but I think it's because it is used to reduce the overfitting. So it's like a setting. It's like a setting that is used to reduce overfitting.
Yeah, the reason why it's a parameter. What is the difference between the main difference between the parameters and the hyperparameters? Who sets the parameters? Who sets the parameters? Do you guys remember that? Did anyone forget the difference between the main difference between the parameters and the hyperparameters? Anyone who think they forgot? Or anyone who think they do not know?
You say, I forgot.
Okay. So the parameters are settings that are set by the model. So the model itself is changing those settings internally. And the hyperparameters are settings that are changed by the person who's working on the project, like the developer, changed by by yourself. So if you change any settings, those can be considered as hyperparameters. So these weight and biases are settings that the model is creating itself. This is why I've said these weight and biases can be considered to be parameters. You understand? So that's what you need to note about those that information. Okay, so the next algorithm will be logistic regression. So logistic regression will be another algorithm, but remember I've mentioned that the logistic regression has nothing to do with a regression problem. So the logistic regression has to do with a classification. Okay, so we will understand more about what you call this, about biases, about what you call bias and weight. I'm just trying to find a video that I can show you so we can just see an example. Let me get a chair. Okay, so we're going to look at this. We're gonna get there when we do deep learning, so we understand what's really happening behind the algorithm. But I would like to show this video so we have an understanding of the concept of weight and biases. Just a second. Let me just share that.
This is a 3. It's sloppily written and rendered at an extremely low resolution of 28 by 28 pixels, but your brain has no trouble recognizing it as a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly. I mean, this, and this are also recognizable as 3s, even though the specific values of each pixel is very different from one image to the next. The particular light...
Okay, guys, are you guys able to see the screen and hear the sound of the video?
Yes, sir.
Okay, so basically this is an example of a project where we use deep learning to recognize handwriting digits. So remember what we said, if we want to recognize something like digits, we only have 10 digits from 0 to 9. So we have 10 classes that's going to be our output. But the inputs are pictures. So each picture will have a size, maybe it's a 28 by 28. So in machine learning, what the machine will do, it's going to take every small pixel of the picture and use it in the calculation of this neural network in order to determine the full picture and determine what number it's at. Okay, so this is now an example of how these pictures as data are going to be used in a neural network, are going to be used in machine learning in order to teach the machine how to detect numbers.
Sensitive cells in your eye that are firing when you see this 3 are very different from the ones firing when you see this 3. But something in that crazy smart visual cortex of yours resolves these as representing the same idea, while at the same time recognizing other images as their own distinct ideas. But if I told you, hey, sit down and write for me a program that takes in a grid of 28 by 28 pixels like this, and outputs a single number between 0 and 10, telling you what it thinks the digit is, well, the task goes from comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural networks to the present and to the future. But what I want to do here is show you what a neural network actually is, assuming no background, and to help visualize what it's doing. Not as a buzzword, but as a piece of math. My hope is just that you come away feeling like the structure itself is motivated, and to feel like you know what it means when you read or you hear about a neural network, quote-unquote, learning. This video is just going to be devoted to the structure component of that, and the following one is going to tackle learning. What we're going to do is put together a neural network that can learn to recognize handwritten digits.
All right, so basically what you see here is when you look at the picture, for example, what you have there, number 7, right? Remember I said we have a picture of a size 28 by 28. So 28 times 28 gives you 784. So each pixel of the picture will be represented in input node. So each pixel will be an input node. As you can see here, if I'm looking at the pixel here in the corner, you can see it's an empty space. All these will be given a value of 0 because there's no shade, there's nothing. But here, they're going to have a certain values that will go from 0 to 1 to show the shade here. So each one will be given that information there. So now this input here, it means that, let's say, for example, this input node here represents 1 point here at the corner. So it's going to be a 0. So you have 1 point here, which is going to be maybe a 0.8, 0.8. So now it's going to take from this. Now, inside here, these hidden layers, the amount of nodes is in the hidden layer. The amount of layers, this will be up to you. That means these are hyperparameters. And then the last layer will obviously be the output layer. In this case, we have 10 categories. Obviously, we are solving a classification problem. Okay.
This is a somewhat classic example for introducing the topic, and I'm happy to stick with the status quo here, because at the end of the 2 videos, I want to point you to a couple good resources where you can learn more, and where you can download the code that does this and play with it on your own computer. There are many, many variants of neural networks, and in recent years there's been sort of a boom in research towards these variants. But in these 2 introductory videos, you and I are just going to look at the simplest plain vanilla form with no added frills. This is kind of a necessary prerequisite for understanding any of the more powerful modern variants, and trust me, it still has plenty of complexity for us to wrap our minds around. But even in this simplest form, it can learn to recognize handwritten digits, which is a pretty cool thing for a computer to be able to do. And at the same time, you'll see how it does fall short of a couple hopes that we might have for it. As the name suggests, neural networks are inspired by the brain. But let's break that down. What are the neurons, and in what sense are they linked together? Right now, when I say neuron, all I want you to think about is a thing that holds a number, specifically a number between 0 and 1. It's really not more than that. For example, the network starts with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its activation. And the image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer of our network. Now jumping over to the last layer, this has 10 neurons, each representing one of the digits. The activation in these neurons, again, some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit. There's also a couple layers in between called the hidden layers, which for the time being should just be a giant question mark for how on earth this process of recognizing digits is going to be handled. In this network, I chose 2 hidden layers, each one with 16 neurons. And admittedly, that's kind of an arbitrary choice. To be honest, I chose 2 layers based on how I want to motivate the structure in just a moment. And 16, well, that was just a nice number to fit on the screen. In practice, there is a lot of room for experiment with the specific structure here. The way the network operates, activations in one layer determine the activations of the next layer. And of course, the heart of the network, as an information processing mechanism, comes down to exactly how those activations from one layer bring about activations in the next layer. It's meant to be loosely analogous to how in biological networks of neurons, some groups of neurons firing cause certain others to fire. Now, the network I'm showing here has already been trained to recognize digits, and let me show you what I mean by that. It means if you feed it an image, lighting up all 784 neurons of the input layer according to the brightness of each pixel in the image, that pattern of activations causes some very specific pattern in the next layer, which causes some pattern in the one after it, which finally gives some pattern in the output layer. And the brightest neuron of that output layer is the network's choice, so to speak, for what digit this image represents. And before jumping into the math for how one layer influences the next, or how training works, let's just talk about why it's even reasonable to expect a layered structure like this to behave intelligently. What are we expecting here? What is the best hope for what those middle layers might be doing? Well, when you or I recognize digits, we piece together various components. A 9 has a loop up top and a line on the right. An 8 also has a loop up top, but it's paired with another loop down low. A 4 basically breaks down into 3 specific lines and things like that. Now, in a perfect world, we might hope that each neuron in the second to last layer corresponds with one of these subcomponents. That anytime you feed in an image with, say, a loop up top, like a 9 or an 8, there's some specific neuron whose activation is going to be close to 1. And I don't mean this specific loop of pixels. The hope would be that any generally loopy pattern towards the top sets off this neuron. That way, going from the third layer to the last one just requires learning which combination of subcomponents corresponds to which digits. Of course, that just kicks the problem down the road, because how would you recognize these subcomponents or even learn what the right subcomponents should be? And I still haven't even talked about how one layer influences the next, but run with me on this one for a moment. Recognizing a loop can also break down into subproblems. One reasonable way to do this would be to first recognize the various little edges that make it up. Similarly, a long line, like the kind you might see in the digits 1 or 4 or 7, well, that's really just a long edge, or maybe you think of it as a certain pattern of several smaller edges. So maybe our hope is that each neuron in the second layer of the network corresponds with the various relevant little edges. Maybe when an image like this one comes in, it lights up all of the neurons associated with around 8 to 10 specific little edges, which in turn lights up the neurons associated with the upper loop and a long vertical line, and those light up the neuron associated with the 9. Whether or not this is what our final network actually does is another question, one that I'll come back to once we see how to train the network. But this is a hope that we might have, a sort of goal with a layered structure like this. Moreover, you can imagine how being able to detect edges and patterns like this would be really useful for other image recognition tasks. And even beyond image recognition, there are all sorts of intelligent things you might want to do that break down into layers of abstraction. Parsing speech, for example, involves taking raw audio and picking out distinct sounds, which combine to make certain syllables, which combine to form words, which combine to make up phrases and more abstract thoughts, etc. But getting back to how any of this actually works, picture yourself right now designing how exactly the activations in one layer might determine the activations in the next. The goal is to have some mechanism that could conceivably combine pixels into edges, or edges into patterns, or patterns into digits. And to zoom in on one very specific example, let's say the hope is for one particular neuron in the second layer to pick up on whether or not the image has an edge in this region here. The question at hand is, what parameters should the network have? What dials and knobs should you be able to tweak so that it's expressive enough to potentially capture this pattern, or any other pixel pattern, or the pattern that several edges can make a loop, and other such things? Well, what we'll do is assign a weight to each one of the connections between our neuron and the neurons from the first layer. These weights are just numbers. Then take all of those activations from the first layer and compute their weighted sum according to these weights. I find it helpful to think of these weights as being organized into a little grid of their own, and I'm going to use green pixels to indicate positive weights and red pixels to indicate negative weights, where the brightness of that pixel is some loose depiction of the weight's value. Now, if we made the weights associated with almost all of the pixels 0, except for some positive weights in this region that we care about, then taking the weighted sum of all the pixel values really just amounts to adding up the values of the pixel just in the region that we care about. And if you really wanted to pick up on whether there's an edge here, what you might do is have some negative weights associated with the surrounding pixels. Then the sum is largest when those middle pixels are bright, but the surrounding pixels are darker. When you compute a weighted sum like this, you might come out with any number. But for this network, what we want is for activations to be some value between 0 and 1. So a common thing to do is to pump this weighted sum into some function that squishes the real number line into the range between 0 and 1. And a common function that does this is called the sigmoid function, also known as a logistic curve.
All right, guys. All these things, we're going to go into them when we go through deep learning, but this was just to show you how the weight is being used. All right, so we have all these algorithms that work differently depending on the scenario that we have. So in this case here, we have the just a second, I'm trying to have this one. So in the logistic regression, so the logistic regression is a classification algorithm. It's not a regression algorithm. So it is a classification algorithm that will determine between categories, all right? So do not be confused by the word regression. Okay. Okay, so I think that is about logistic regression. And then we have, we spoke about linear regression, spoke about logistic regression, and then we have other algorithm as well, such as the softmax function. So basically, the softmax function is just a function that will be used mostly when we have a multi-class classification problem. But if we have a binary classification where we finding between two, we're going to use logistic regression. All right. So what it does is that you have, for example, the softmax function here. What it does is whatever calculation is going to do with the data is going to output. What is it? This model. It's going to output the probability of that. For example, we have here a picture of an apple. I'm not sure why this keeps moving. Okay, the picture of an apple here. From this picture, the machine can be able to look at and say there's a 9% probability of this being a grape, 22% orange, and so the highest percentage will be the information that will be output. Okay. So another algorithm will be the decision tree. So the decision tree, the way it works, it's mostly of it's also used in multi-class classification. So basically, the way the algorithm works, it looks at all the features and find the relationship between features to determine, to classify whatever information we have. So how does it go? We have what we call the leaves. Okay, we first have the root. So in the decision tree, the root is at the top, not like a normal tree where the root is at the bottom. No, here the root is at the top. So we have the first problem that is solved. So in this example here, we have an animal with the branches showing, okay, if the animal is short, then what's the option? It can be a squeak or it cannot be a squeak. Okay, it can squeak. If yes, might be a rat. A rat cannot squeak, might be a squirrel. Okay, so and then we have tall, long neck, short neck. You know, all these just to try and determine what we have as an output based on the answer that we get from this tree. Okay. All right, so this is how the structure is. We have the root node at the top. Remember that. And then the output nodes are called the leaf node. And then the internal nodes are just the internal question, the internal steps that will determine the next step. All right. So these are some key points of the decision tree construction. So the way we construct it, I've spoken about it again. We start from the top, and the top represents the root node. Okay. You need to note there is a few algorithms out there that are decision tree algorithm. We have the ID3, the C4.5, and the COT. Okay, so the process will be to select the features, and then to build a decision tree to generate it. We will take the internal node upside down based on the selected features. So we look at the features and then we create the tree like that by remembering that the root node is at the top, and then we ask ourselves questions based on what we're trying to predict. Okay. Okay, so here's an example here. So in this example, we have a classification problem where we've used a decision tree. So the classification, so what we need to check is if someone can cheat based on, you have the refund, the marital status, and the taxable income. So we have here, these are the data that we were given. So we have yes, single, 125,000, no. And then no, married, 1,000, no. You understand this? So now how do we construct it? Remember the process, what we say. First, selection of features. So what are the features here? We're going to have the refund, the marital status, and the taxable income. So, and then the way we want to generate it, We generate the internal node upside down based on the selected features and stop until the data set can no longer be split. So what we do here, we start from here, the refund, if it's yes, we check there's a yes and a no. So we check based on this information. Every time we have a yes refund, the cheat is always no. Yes refund, no, no. This is how we're gonna build this. And then we ask marital status, married or single divorce. Then we have that. That is a decision tree. Okay, so another algorithm will be the SVM, support vector machine. So the SVM is an algorithm that is mostly used in classification problem, but mostly in binary classification problem. Okay, guys, please tell me what's the difference between a binary classification and a multi-class classification problem? What's the difference? Guys, please, what's the difference between a binary classification and a multi-class classification problem? Guys, can you hear me? Why you guys are so quiet? Can you guys hear me?
Yes, sir.
Oh, okay. So I'm asking, what's the difference between a binary classification and a multi-class classification? Guys, this should be a question that everyone can answer. What is the difference?
Oh, sorry, sir. Binary has only like two options. You can choose between two options, and multi has main options, more than two options.
Yes. It just means that binary classification problem, the output of our learning, the outputs is you only have two options, and a multi-class means you have multiple options. So a binary classification can be to detect between men and women. You see? So and the multi-class can be to detect between maybe 5 fruits that you have there. So if you have a problem where you are trying to solve a binary problem, you can use SVM as your algorithm. Someone else can say they're going to use logistic regression because it can also solve a binary classification problem. You see, this is what I said. You need to identify the problem, know what you're solving, and see which algorithm can solve that problem. So this is an example of the support vector machine. This algorithm will just divide the data into two groups based on the similarities. So the more, so it creates this model, which is a model that will divide this into two. So the output of a binary classification. So, okay, so now when we have these two groups of data here, if we ask you to divide this data, someone else can create a line just like this. Someone else can create a line like this. So which one will be the right model? Obviously, there is someone who can get a perfect model here. So what do we do? That's where we have all the options that we have. So this is an example where we have so many models that can solve this problem. But this algorithm, the way it's going to be constructed, it's going to be constructed in order to find this type of model, which means you have the model which has data that are closer to the model on a certain extent, depending on the amount of data that we have. Okay. So this is an example of when the data are not really placed in the right order. We can have this as well. We create what we call a kernel. So the kernel is going to help you take those data and put them in a certain plane to divide them properly, like this. So the kernel is taking this data and put them into this. Okay. So this can be an example of using SVM. It can be used in a scenario where you're trying to detect people's mood, right? If they are surprised, they are angry, they are sad, they are happy, you know, all this. Okay. Another algorithm will be the KNN, the KNN classification algorithm. This is also used in classification. This is just a method of in machine learning where we can divide the elements based on a certain numbers of similarities that we want. So we can create a certain group. We say we want to divide the data into 3 classes. So based on the similarity of the data's features, we classify them into 3 classes. Okay. So that's why it's called the K nearest neighbor. So the nearest neighbor has to do with the similarities. Okay. So this is an example of how the KNN can be used, where we have, remember here now, we try to detect between cat and dogs, but you have a small puppy. A small puppy can easily be identified as a cat. You see, so you have those challenges. So the KNN can be used in this scenario where you train the data to understand how to detect dogs and then understand how to detect cats. So whenever you bring a new data, it can take it to category B or category A based on the majority of features of that image. So when you have here, your classifier here that you create, your model understand this type of pictures. But when you bring this picture here, which does not really show the same one here, but because of the similarities of features, the classifier will classify this as a cat. It's going to predict this output as a cat. So the KNN is a K nearest neighbor. So it's basically it like think of you when you cannot see an animal, but you will classify the animal based on the similarities and say this animal look like another animal. You may think that's the animal. So that's exactly what the machine will do. Okay, and then we have an algorithm called the naive Bayes algorithm. The naive Bayes algorithm is called naive Bayes algorithm because it's a very weak algorithm that just look at the probabilities based on the similarities. You know, simple features can be detected and your object will be classified as a certain object because of just simple similarities. So that's why they call it the naive Bayes, because the algorithm that is really naive. So the naive Bayes can look at an example such as a fruit like that. It look at a fruit because it's red, it's round, and it's about 10 centimeters, and the algorithm will detect it as an apple. So it's not even going to do further research or things like that. Okay, so those are algorithms, some of the algorithm, and we have a method called, this is just a method called ensemble learning. So ensemble learning means that when you have so much data set, you can have a big project. Instead of creating one model, you can actually take a certain group of data sets, create a model, take another group of data set, another data set, you create another model, and then you take another data set, you create another model, you create as many models as you want, and then you take a model combiner and combine all the models together and get the final model. So that is just a method. Ensemble learning means that we are creating a model by dividing the data and creating multiple models. Okay, so in the ensemble learning method, we have two different ways of doing it. You can either do that with what we call a bagging or boosting. So some algorithms were created using bagging, such as the random forest. Okay, so how does it work? So you basically build several learners, then average the prediction. So as you see here, so we have all these models here, and then we see we can find an average of the prediction, and that will give us our final model. Okay. Okay, so and then we have the boosting. The boosting, we have some examples such as the ADA boost, the GBDT, the XG boost. So these algorithms here, the way they work is that they construct basic learners or those models. They construct them in a sequence to gradually reduce the bias of the composite learner. So basically, in that case, we're going to have this model. The output of this model is going to help us to build this model. And whatever we get from this model, it's going to help us build the next model. And then we are reducing the bias that way. Okay. So these are examples of ensemble method in machine learning. In this case, we've used to create a random forest, we need a bagging and cut decision tree. You see, remember we spoke about decision tree. So if you take a cut decision tree plus a bagging method, you can obtain a random forest algorithm. Okay, and then we'll have the GBDT is also a type of boosting algorithm. So this one will use the boosting algorithm. It means whatever we're going to get as a prediction of the first, it affects the second one, it affects the third one. So we basically create a model like that. Okay, so in terms of unsupervised learning, we have some algorithms that work with unsupervised learning, such as the K-mean. Remember now here, we don't confuse the K-means and the KNN. The KNN, K nearest neighbor, that one is a classification algorithm. And then the K-means is a clustering algorithm. Here, we're not going to create just really determine what data represent, but we're just going to create a K to say how many groups we want our algorithm to classify our data. Okay, and then the last one will just be another unsupervised learning would be the hierarchical clustering. Okay, so which will, in this case, it's going to divide the data set into different layers and form kind of a decision tree clustering structure. Okay, so this is an example here where we have data, we have cars like this, and then it's kind of every decision tree is going to classify them based on the similarities, create another class, and then keep on dividing until we get to the last option. All right, guys, tomorrow we're going to go through this case study where we're going to solve this issue using no, I'm not going to say which algorithm we're going to use because tomorrow we will have to solve it together. All right, guys. I think that's it about today. Any question? Any question? Yes. Yes. What's the question?
Oh, thank you, sir. It's not about our class today. I wanted to understand something about the upcoming exam. What did you mean by saying the exam will be on site?
Okay. Why you have to register by saying on site, right?
Okay.
It's because if you say online, the platform